Welcome to one more video on linear integrated circuits. In this video, we shall see one of the application of Opamp, that is a stable multimeter. We shall see the basics of a stable multimeter. Now, this is the conceptual uh, representation of a stable multimeter. Now, as you can see here, so here we have a Smith trigger-like circuit, and we have a capacitor charging, discharging, feedback path. So, as you can see now, the Smith trigger output is always going from plus Vset and minus Vset, and this capacitor is charged to this plus VCC and minus VCC. So now you can see this is how the capacitor is charging towards plus VCC and towards minus VCC. Now we know that when the input of a Smith trigger exceeds VTH, the output changes from plus Vset to minus Vset. Now on its way towards minus VCC here, you can see when the capacitor is charging towards minus VCC, but when it crosses VTL, whenever it crosses VTL, the output again changes from minus Vset to plus Vset. Meaning the input to the Smith trigger is not given from an external source. The input to the Smith trigger, which is a part of the astable multimeter, will get the input from the capacitor charging and as well as discharging. This is the input for the Smith trigger. So as you can see here, so we are not connecting any external input. The input is actually the capacitor charging and discharging. So as the capacitor tries to exceed VTH, output makes a transition from plus Vset to minus Vset. So whenever the output is minus Vset, capacitor starts discharging, but when it tries to go below VTL, the output again changes from minus Vset to plus Vset. So like this is keep on repeating. So that's why this astable multimeter. Astable multimeter is also called as a free-running oscillator because it oscillation never stops. It doesn't require any trigger signal. So output is either plus Vset or minus Vset, which is the output of a Smith trigger. Now this is the actual circuit diagram of the Smith trigger, as you can see here. So we have the Opamp, and this R1, R2 are used for providing that positive feedback. I can see if you carefully observe with R1 plus R2 connected to the inverting terminal, and this inverting terminal, suppose if it is connected to an input source, and this would have been look like a Smith trigger, that is inverting Smith trigger. Now instead of connecting the source here, the input for this inverting terminal is being obtained from this capacitor charging towards V0 through a resistor R. Now as you can see the waveforms here, assume that the output voltage is plus Vset. So assume that V0 is plus Vset. Whenever it is plus Vset, so assuming now you can see the capacitor is charging. So the capacitor is keep charging towards VCC. So the output will be at plus Vset, which is over here. The output is now charging towards plus Vset. So on its whenever the output is plus Vset, we can see the output voltage, the voltage at V plus is beta Vset. So this is beta Vset, which is given by, so beta is nothing but R1 divided by R minus R2. The voltage at V plus is VTH. So when V0 is plus Vset, the V plus is beta Vset. The capacitor now charging towards VCC. On its way towards VCC, whenever it exceeds the beta Vset, this voltage will become more than this. When V minus is greater than V plus, we know that the output makes a transition from plus Vset to minus Vset. So likewise, whenever it tries to exceed VTH, the output makes a transition from plus Vset to minus Vset. Once it is minus Vset, capacitor is now discharging towards the minus Vset. So on its way towards minus Vsat, whenever it crosses VTL, like it is also necessary to observe whenever the output is minus Vsat, the voltage at the non-inverting terminal will become minus beta Vsat. So this is VTL, this is beta into this L minus corresponds to minus Vsat. So the voltage at the non-inverting terminal will be either plus beta Vsat or minus beta Vsat depending on what is the output voltage. Now let's see the working of the astable multiplier in detail in different stages. Let us assume stage 1 where the output voltage is plus Vsat. So this is plus Vsat. Now the capacitor is charging towards VCC. Now the capacitor is, this is stage 1. The capacitor is charging towards VCC. The voltage at the non-inverting terminal is plus beta VCC. Now the voltage at the inverting terminal is the capacitor voltage. Now that's what we saw in the circuit diagram. As long as the capacitor voltage is less than plus beta VCC, the output remains in plus Vsat, meaning when the capacitor voltage is in this region 1, which is less than VTH, the output remains in plus Vsat. That's what is initial stage is plus Vsat, the capacitor remains to be there in, output voltage remains to be there in plus VCC as long as the capacitor voltage is less than VTH. Now assume that the output voltage is, this is stage 2, exactly at this one. Assume that output voltage is plus VCC, that's what is here. Now capacitor will keep on charging. The voltage at the non-inverting terminal is plus VCC. Suppose if the capacitor charges, the capacitor voltage is slightly greater than beta VCC, you can see when it is slightly greater than beta VCC, then V minus will become, as you can see here, the V minus becomes more than V plus in this second stage. Whenever V minus becomes greater than V plus, the output makes a transition from plus Vsat to minus Vsat. That's what is happening at stage 2 here. This is stage 2 only at this instant. Now the output has become minus VCC. So that's what is this third stage. In the third stage, the output is minus VCC. Now the capacitor is discharging towards minus VCC. So whenever the output is minus VCC, the voltage at the non-inverting terminal will become minus beta VCC. So now you can see the voltage at V plus is minus beta VCC and the capacitor is now charging towards minus VCC now. So as long as assume that this is minus 5 volts, if this is minus 2, minus 1, minus 3, minus 4, meaning that this voltage is certainly more than this. So as long as the capacitor voltage is more than minus beta VCC, output remains to be there in minus Vsat, not minus VCC. So it is still remaining in minus VCC. That is in stage 3. But on its way towards minus VCC, when the output voltage is minus VCC, the capacitor is still discharging towards minus VCC. The voltage at non-inverting terminal is minus beta VCC. If the capacitor voltage tries to go below minus beta VCC, that is VTL, you can see if it is less than that, then it's exactly at 4. At 4 means at this juncture, if it tries to go less than minus beta VCC, the output makes a transition from minus Vsat to plus Vsat. You can see now it is going from minus Vsat to plus Vsat. So this is 4 stages. While charging, the output voltage is plus Vsat. If the capacitor voltage exceeds VTH, the output changes to minus Vsat. If changes to minus Vsat, the capacitor is start discharging, and on its way towards minus VC while discharging, if the capacitor voltage reduces below VTL, it again starts charging. I can see the circuit diagram. So capacitor will charge towards V0 through R. If the capacitor is asked to discharge towards minus VCC, it will again discharge through R. So you can see capacitor charges towards plus VCC through R with a time constant RC. The capacitor discharges towards minus VCC again through R with a time constant RC. Meaning, while charging and discharging, the capacitor path is only through R and its time constant is R into C. We can actually obtain the expression for T1, TH, that is T on. So H stands for high here. Expression for T on is given by, we know this capacitor expression, and assuming that the capacitor settled down, the initial voltage during TH, as you can see, this is the initial voltage at T is equal to 0 for TH. So at this point of time, the capacitor initial voltage is minus beta VCC. Finally, it is allowed to go up to VCC, but at T is equal to TH, the capacitor voltage is plus beta VCC. Substituting these things in this equation and rearranging, we get T on or TH is equal to RC ln of 1 plus beta by 1 minus beta. Usually this ratio is always greater than 1. So if we have this value of beta depends on the values of R1 and R2. So actually beta is R1 divided by R1 plus R2. So that is true only if the resistance are connected. This is R1 and this is R2. It's actually beta is this resistor divided by R1 plus R2. That is sum of the two resistors. Similarly, we can find the expression for the off time, that is TL. So while finding TL, so we need to take the initial capacitor voltage as plus beta VL. The final voltage is minus VCC. At T is equal to TL, the capacitor voltage becomes minus beta VCC. So substituting all those things, we again solve that, and the off time or the TL becomes again RC into ln of 1 plus beta divided by 1 minus beta. So it is carefully you can observe the off time and the on time both are same because it is charging and discharging towards plus VC minus VCC through the same resistor with same time constant. That's why on time is equal to off time, meaning that using this circuit we can get duty cycles only 50%. So that's what is the design of a square wave. In type 1 we are assuming the value of R1, R2, and you can see if R1 and R2 are 1K, 1K, the resistor, the timing resistor happens to be 1 kilo ohm, and the value of C given is these values. So we can estimate the value of beta. We can find what is the on time and of course the frequency. So R1, R2 are same here. So okay, sorry, this R1, R2 will decide the value of beta. This R will decide the timing the resistor C is using the timing capacitor. This R1, R2 will going to decide what the value of beta. You can see beta is 0.5, beta is 0.09, the beta is 0.9, the value of beta is again 0.09, here it is 0.4, this R1, R2, and this R is the timing resistance. So this R is required to find the T on or T off, which is nothing but RC into ln of 1 plus beta by 1 minus beta. So using these specifications we can actually obtain what is the on time and off time. This is one type of design where the resistance are given, you can find the on time, off time. The other one, so you have been, the specification given is what is the values of on time, off time required. The value of beta is given, the value of resistor is given. We are asked to estimate the values of R1, R2 and C. This is your timing capacitor. In the third possible design, we are asked to design a stable multimeter with a given frequency, duty cycle, the value of timing capacity is given, beta is given. So we can assume, we can actually estimate the other parameters like okay, what is R1, R2 and the timing resistor. So with these specifications, with the value of beta, by assuming the value of R2, we can find out what is R1 and the value